Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar.
Hello everyone. Welcome to lecture 27 of the course Marine Renewable Energy Systems Analysis, Design and Development. I am Dr. Basangoda I. Patil, Assistant Professor, Department of Civil Engineering, PDU, Gandhinagar, Gujarat. In the previous lecture, we discussed the fundamentals of power takeoff systems and examined the major PTO technologies used in wave energy converters, including mechanical, hydraulic, pneumatic, electrical and direct drive generator systems. In today's lecture, we will begin our detailed study of the first PTO category, namely mechanical PTO systems. We will understand the working principles of mechanical PTOs, explore common motion conversion mechanisms such as geared trains, rack and pinion, crank slider arrangements and flywheel based energy storage systems, and discussed their advantages, limitations and practical applications in wave energy converters. By the end of this lecture, you will have a clear understanding of how mechanical systems convert wave induced motion into useful rotational motion for electricity generation. So, let us begin with the fundamental concept of a mechanical PTO system. A mechanical PTO system is a mechanism that converts wave induced mechanical motion directly into rotational or translational mechanical energy before electrical conversion. As we know, ocean waves cause continuous motion of floating bodies. Oscillating structures or articulated components of a wave energy converter. However, this motion cannot directly power conventional electrical generators in most cases. Therefore, an intermediate mechanism is required to transfer and modify the motion. This is where a mechanical PTO system plays an important role. The primary function of a mechanical PTO is to capture the motion produced by waves and mechanically transmit it to another component, usually a rotating shaft connected to an electrical generator. Mechanical PTO systems are characterized by direct mechanical transmission instead of using hydraulic fluids or compressed air. The energy is transferred through physical mechanical components. Some of the most commonly used mechanical components includes gears, levers, rack and pinion mechanisms, crank sliders systems, chains, sprockets and flywheels. For example, if a floating buoy moves up and down and due to a wave action, a rack and pinion mechanism can convert this vertical motion into rotational motion. Similarly, crank mechanisms can convert reciprocating motion into continuous shaft rotation suitable for electricity generation. One important advantage of mechanical PTO system is their simplicity in the design. The operating principle is relatively easy to understand, design and manufacture. Because of this, mechanical PTOs were among the earliest PTO concepts proposed for wave energy converters. Historically, many early wave energy devices relied heavily on mechanical transmission systems because they were based on well established engineering technologies already used in machinery, automotive systems and industrial equipments. However, as we will see later in this lecture, mechanical PTOs also face certain challenges, particularly related to wear fatigue, lubrication requirements and maintenance of moving components operating in harsh marine environments. Nevertheless, understanding mechanical PTO systems is important because they provide the foundation upon which many other PTO technologies have evolved. In the next slide, we will examine the basic energy conversion pathway of a mechanical PTO system. And understand how wave motion is transferred into useful rotational motion for power generation. Now that we understand what a mechanical PTO system is, the next logical question is, why do we use mechanical PTO system in wave energy converters? Okay. Mechanical PTO systems were among the earliest technologies explored for wave energy conversion because of their simple design, as I have told before, and practicality. The first stage and first advantage here is that simple working principle. The energy transfer process is straightforward. Wave induced motion is captured and transmitted through mechanical components such as gears, levers, chains, crank mechanisms, flywheels. Engineers are already familiar with these mechanisms because they are widely used in conventional machinery. So, it is simple working principle, direct motion transfer and lower initial complexity and easy conceptual design. The second advantage is the direct motion transfer. Unlike hydraulic PTOs, which require fluid circuits, pumps, accumulators and motors, mechanical PTOs transfer energy directly from the moving structure to the generator. This can reduce energy losses associated with the intermediate conversion stages. Another benefit is lower initial complexity. Since the system relies mainly on mechanical linkages and transmission elements, the overall design is often easier to build and test, especially during the early stages of technology development. Mechanical PTO systems also offer easy conceptual design. Researchers can quickly develop laboratory prototypes and experimental models using commercially available mechanical components. This makes them particularly attractive for academic research and proof of concept studies. Because of these advantages, mechanical PTOs have found applications in several areas. They are commonly used in small scale wave energy converters, where simplicity and low cost are important considerations. They are also widely used in prototype systems, where researchers want to validate concepts before moving toward more advanced PTO technologies. In addition, many educational and experimental devices employ mechanical PTO mechanisms because the energy conversion process is visible and easy to understand, making them valuable teaching tools. However, it is important to note that while mechanical PTO systems are simple and effective, they may face challenges related to wear, fatigue, lubrication and maintenance, particularly in offshore environments such as seawater. So, we will discuss these limitations later in the lecture. At this stage, it is sufficient to understand that mechanical PTO systems remain an important category of wave energy conversion technology because of their simple design, robustness and ease of implementation. Let us understand now the basic energy conversion mechanism of a mechanical PTO. The flowchart on the screen shows how energy is transferred from ocean waves to electrical power. The process begins with wave motion. Ocean waves contain both kinetic and potential energy, which causes wave energy converter to move continuously. This wave induced movement creates mechanical oscillations in the device. Depending on the type of wave energy converter, this oscillation may be in the form of heave, pitch, surge or relative motion between different bodies or different connecting structures. The next stage is the mechanical transmission system. This is the core of a mechanical PTO. Components such as gears, rack and pinion mechanisms, crank sliders, chains or flywheels are used to transfer and transform the oscillatory motion. Most electrical generators operate efficiently with continuous rotational input. Therefore, transmission system converts the irregular oscillatory motion into a rotational motion. This rotational motion is then supplied to an electrical generator where electromagnetic induction converts mechanical energy into electrical energy. Therefore, the complete energy conversion pathway can be summarized as wave motion induces mechanical oscillations, which transmits and induces rotational motion, then it drives the electrical generators. An important point to remember is that the mechanical PTO acts as an intermediate energy transmission mechanism, bridging the gap between wave induced motion and electricity generation. The effectiveness of this intermediate stage largely determines the overall performance and efficiency of the wave energy converter. Let us now examine the major components that constitute a mechanical PTO system and understand how energy flows through the system from ocean waves to electricity generation. The schematic shown on this slide illustrates the complete energy conversion pathway. The process begins with incident waves. Ocean waves contain kinetic and potential energy and which serves as the primary energy source for the wave energy converter. The second component is a floating wave energy converter body, also called as floating wake. As wave passes, the floating structure experiences motions such as heave, pitch or surge. These oscillatory motions contain the mechanical energy that we want to extract. The next element is the linking system, which may consist of rods, levers, articulated joints. The purpose of the linkage is to transfer motion from the floating body to the PTO mechanism while maintaining structural integrity. One of the motion reaches the PTO is often processed through a crank slider mechanism or a rack and pinion mechanism. A crank slider mechanism shown here converts reciprocating motion into rotary motion, similar to the operation of an automobile engine. A rack and pinion mechanism performs a similar function by converting linear motion into rotational motion through the interaction of the gear and a toothed rack. The resulting rotational motion is then transmitted to a gear, train or a motion amplifier. This component is extremely important because wave induced motions are usually slow and irregular. Electrical generators, however, require higher rotational speeds for efficient operation. Therefore, the gear train increases rotational speed and adjusts torque to suitable levels. Following the gear train, many systems incorporate a flywheel. The flywheel acts as a temporary energy storage device because ocean waves are naturally irregular. The power input fluctuates continuously. The flywheel stores energy during high input periods and releases it during low input periods, helping to smooth the rotational speed and improve generator performance. The next stage consists of shafts, bearings, and couplings. These components transmit rotational motion from one element to another while minimizing frictional losses and ensuring proper alignment of the system. Finally, the rotational energy reaches the electrical generator. This generator converts mechanical energy into electrical energy through electromagnetic induction, producing useful electric power. So, if we summarize the complete process, incident waves hits the floating wake and it oscillates. Then the linkage system such as crank slider, rack and pinion helps in rotating the gears and the flywheel. Then shaft and bearings helps in rotating the generator, then the electrical output is achieved. Now let us briefly discuss the key features highlighted on this slide. Mechanical PTO systems are generally simple and robust. They are suitable for low speed and high force wave motions. Their performance largely depends on the quality of the transmission design. Proper lubrication and maintenance are important because multiple moving components are involved. The inclusion of a flywheel can significantly improve power smoothness and reduce fluctuations. The main idea to remember is that mechanical PTO systems rely on well established mechanical engineering principles to transform irregular wave motion into controlled rotational motion that can efficiently drive an electrical generator to produce power. Let us understand one of the most widely used mechanical transmission mechanism in wave energy converters, the crank slider mechanism. The primary purpose of a crank slider mechanism is to convert oscillatory linear motion into rotary motion. This is particularly useful in wave energy applications because the motion produced by waves is usually an up and down or back and forth movement, whereas electrical generators typically require continuous rotational motion for efficient operation. So, let us understand the working principle shown in the figure. When the wave hits or causes the buoy or floating body to move, linear displacement is generated. This displacement is transmitted through a connecting rod. The connecting rod is attached to a crank pin which is mounted on a rotating crank wheel. As the connecting rod moves back and forth, it forces the crank wheel to rotate. In this manner, the reciprocating motion generated by the wave action is transformed into electrical motion that can drive a generator. This principle is identical to the mechanism used in internal combustion engines, where the reciprocating motion of pistons is converted into rotational motion of the crankshaft. Because of its simplicity and effectiveness, crank slider systems have been used in several wave energy devices. Typical applications includes point absorber wave energy converters, mechanical PTO systems, oscillating type buoy devices. Now, let us discuss the advantages of this mechanism. The first advantage is its simple motion conversion, and the mechanism is well understood and has been used extensively in mechanical engineering applications. The second advantage is efficient transmission for moderate motion amplitudes, for making it suitable for many laboratory scale and prototype wave energy systems. However, there are also some limitations. Since several moving joints are involved, wear can occur at joints such as bearings and connections over time. In addition, wave energy systems operate under continuous cyclic loading, therefore, fatigue damage can accumulate in the mechanical components if they are not properly designed and maintained. This brings us to the efficiency consideration shown on this slide. The overall efficiency of a crank slider PTO is strongly influenced by bearing and joint friction at joint losses. Proper lubrication and regular maintenance are therefore essential. In some designs, a flywheel is added downstream of the crank mechanism. The flywheel helps smooth fluctuating rotational speed caused by irregular waves and provides a more suitable input to the generator. Overall, the crank slider mechanism remains one of the most practical and intuitive approaches for converting wave induced linear motion into useful rotational motion for electricity generation. Let us now discuss another widely used mechanical PTO mechanism known as the rack and pinion systems. The rack and pinion arrangement is one of the simplest and most efficient methods for converting linear motion into rotational motion. The basic working principle here is straightforward. A wave passes through the device, the buoy experiences an up and down motion. This motion drives a rack, which is a straight toothed component here. The rack is engaged with a rotating gear called a pinion. As the rack moves vertically due to wave action, the teeth of the rack force the pinion gear to rotate. In this way, the linear displacement generated by the wave is directly converted into rotational motion. This rotational motion can then be transmitted through the shafts and gears to drive an electrical generator. The figure on this slide illustrates this concept. The buoy moves with the wave, causing the rack to move vertically, while the pinion converts that motion into continuous rotation to power generation. Because of its simplicity, the rack and pinion mechanism has been used in several wave energy devices. Typical applications includes point observer wave energy converters, heaving buoy systems, direct mechanical PTO devices, and floating oscillatory wave energy converters. One of the major advantages of rack and pinion systems is their high piston, high pinion systems is their high mechanical transmission efficiency. Typically, around 95 to 98% gear mesh efficiency under proper lubrication, making this mechanism very attractive for energy conversion applications. However, there are also some engineering challenges. Since gear and teeth continuously engage and disengage under cyclic wave loading, gear tooth wear can occur over time. Another issue is backlash, which refers to the small clearance between the mating gear teeth. Excessive backlash can lead to vibration, noise, and loss of transmission accuracy. In offshore environments, corrosion becomes an important concern because gears and mechanical components are exposed to moisture, salt spray, and harsh environmental conditions. Therefore, regular inspection, lubrication, and maintenance are necessary to ensure long-term reliability. As highlighted on this slide, the efficiency of a rack and pinion PTO depends on several factors, including gear tooth profile, alignment accuracy, lubrication quality, and bearing losses. Even if the rack and pinion mechanism itself is highly efficient, the overall PTO efficiency is also influenced by losses occurring in bearing and coupling. Overall, rack and pinion systems offer an elegant and highly efficient solution for converting wave-induced linear motion into rotational motion and remain one of the most popular mechanical PTO technologies in wave energy research. One of the major challenges in wave energy conversion is that ocean waves are highly irregular. The energy available from waves continuously varies with wave height, wave period, and sea conditions. As a result, the rotational speed delivered to the generator can fluctuate significantly. To address this problem, many mechanical PTO systems incorporate a flywheel. A flywheel is essentially a rotating mass that stores energy in the form of rotational kinetic energy. The basic idea is very similar to a rechargeable battery, except that instead of storing electrical energy, flywheel stores a mechanical energy. During periods of high wave activity, when more energy is being captured than the generator immediately requires, the excess energy is stored in the flywheel by increasing the rotational speed. Later, during periods of lower wave energy or lower wave excitation, when the wave energy input decreases, the flywheel releases part of the stored energy. This process helps maintain a more stable rotational speed and provides a smoother power output to the generator. This is particularly important because electrical generators generally operate more efficiently under steady rotational conditions than under rapidly fluctuating speeds. The figure shown on this slide illustrates a flywheel integrated mechanical PTO system. Starting from the wave energy converter, the captured mechanical motion is transmitted through shafts, gears, bearings and springs before reaching the flywheel. The flywheel acts as an intermediate energy storage element and finally delivers a smoother rotational input to the electrical generator. Flywheel systems have been used in mechanical PTO systems, point absorber wave energy converters, oscillatory buoy systems and hybrid energy storage PTOs systems. Now, let us discuss more limitations, some more limitations. Because of because a flywheel is a rotating mass, it includes or introduces additional weight and inertia into the system. The rotating shaft and bearings can also introduce bearing losses, which reduce overall efficiency. Another challenge is the space requirement, particularly for offshore devices where compact designs are often preferred. Finally, the structural design must safely withstand the centrifugal forces generated during high speed rotation. Despite these challenges, flywheels remain an effective solution for reducing power fluctuations and improving generator speed stability. The key takeaway from this slide is that a flywheel does not generate energy, rather it temporarily stores and releases energy to smooth the highly variable nature of wave power. Let us now discuss the role of gear transmission systems in mechanical PTOs. One of the major challenges in wave energy conversion is that the motion produced by ocean waves is generally characterized by low rotational speed and high torque and continuously varying excitation conditions. However, electrical generators typically operate most efficiently at much higher rotational speeds. This creates a mismatch between the energy source and the generator. Gear transmission systems are introduced to bridge this gap. The primary purpose of a gear train is to convert the slow high torque motion coming from the wave energy converter into a faster rotational motion that is suitable for electricity generation. In other words, gears acts as a speed amplification mechanism. Besides increasing shaft speed, gear trains also help match the operating requirements of generators and improve the overall effectiveness of energy conversion. Several types of gears are commonly used in PTO systems. The simplest is the spur gear, which consists of straight teeth mounted parallel to the shaft axis. Spur gears are easy to manufacture and typically exhibit very high efficiency. Another commonly used type is the helical gear, where the teeth are inclined at an angle. Helical gears operate more smoothly and quickly than spur gears and are often preferred when vibration reduction is important. For applications requiring compact designs and high gear ratios, planetary gear trains are frequently employed. These systems can achieve large speed increase within a relatively smaller space. In some advanced PTO systems, multi-stage gear are increasers are used to achieve the high rotational speeds by generators. Now, let us look at the efficiency values shown in the table. Typical gear efficiencies are very high compared to many other mechanical components. Spur gears generally operate at efficiency of approximately 97 to 99%. Helical gears typically achieve efficiencies of 96 to 98%. Planetary gear systems usually generate or operate between 95 to 98%. These values demonstrates why gear trains remain one of the most effective methods to mechanical power transmission. However, it is important to remember that the overall PTO efficiency depends not only on the gears themselves but also on bearing losses, shaft alignment, lubrication quality, and maintenance practices. The key takeaway from this slide is that gear transmission systems play a crucial role in transforming slow wave induced motion into generator compatible rotational speeds while maintaining very high energy transmission efficiencies. Let us now discuss an important concept in mechanical PTO design known as motion amplification. One of the fundamental challenges in wave energy conversion is that ocean waves typically produce low frequency oscillatory motions. In other words, the motion generated by waves is generally slow, irregular, and characterized by high force but relatively low speed. However, most conventional electrical generators are designed to operate efficiently at much higher rotational speeds. This creates a mismatch between the characteristics of the wave energy source and the operating requirements of the generator. To overcome this challenge, mechanical PTO systems incorporate motion amplification such as gear trains, lever systems, pulley arrangements, crank mechanisms, and other transmission devices. The objective is to increase the rotational speed delivered to the generator while the generator appropriately transforming the available torque. In simple terms, motion amplification converts slow rotational speed and high force input into a faster rotational output that is more suitable for electricity generation. This concept is extremely important because without proper motion amplification, the generator may operate at low efficiency and produce significantly less electrical power. From an engineering perspective, motion amplification offers several benefits. First, it improves generator utilization, allowing the generator to operate closer to its optimal speed range. Second, it enables more efficient conversion of wave induced mechanical motion into electricity. Third, it helps match the characteristics of the PTO system with the operational requirements of the electrical generator. Therefore, motion amplification serves as a critical bridge between the naturally slow motion of ocean waves and the higher speed requirements of modern power generation equipment. The key takeaway is that the purpose of motion amplification is not to create additional energy, but to transform the available mechanical motion into a form that can be utilized more effectively by the generator. Up to this point, we have discussed various mechanical PTO components such as crank slider mechanism, rack and pinion systems, flywheels and gear trains. However, regardless of how sophisticated a PTO system is, not all the captured mechanical energy reaches the generator. Some portion of the energy is inevitably lost during transmission. This brings us the concept of mechanical efficiency. Mechanical efficiency represents the fraction of mechanical power that is successfully transmitted through the PTO system. Mathematically, it is defined as eta m is equal to P output divided by P input into 100, where P input is mechanical power entering the PTO, P output is mechanical power delivered to the generator, and eta m represents the mechanical efficiency expressed as a percentage. For example, if 100 watts of mechanical power enters the PTO and only 90 watts reaches the generator, the mechanical efficiency is 90%. The difference between the input and the output power represents the losses occurring within the PTO system. Let us now discuss the major sources of these losses. The first source is friction losses. Whenever two mechanical components move relative to each other, friction is generated. Examples include sliding surfaces, rotating shafts, gear contacts and moving joints. These frictional effects convert useful mechanical energy into heat. Poor lubrication generally increases friction losses and reduces efficiency. The second source here is bearing losses. Bearings are essentially components that support rotating shafts. Although bearings reduce friction significantly, they do not eliminate it completely. Energy is continuously dissipated within bearings due to rolling resistance and internal friction. These losses depend on factors such as rotational speed, bearing type and maintenance condition. Over time, bearing degradation can gradually reduce transmission efficiency. Another important source is gear meshing losses. When gears transmit power, the gear teeth slide and roll against one another. Although gear efficiencies are generally high, some energy is still lost because of tooth contact friction. The magnitude of these losses depends on gear geometry, lubrication quality and manufacturing precision and alignment. The next category is misalignment losses. If shafts, couplings or bearings are not properly aligned, additional resistance is introduced into the system. Even small alignment errors can increase vibration, accelerate wear and reduce long-term efficiency. Finally, we have fatigue and wear losses. Wave energy converters operate under continuous cyclic loading. Over thousands or even millions of loading cycles, components gradually wear out, surface roughness increases, clearness develop and transmission efficiency decreases. This is one of the major reasons why reliability and maintenance are critical considerations in offshore wave energy systems. The key message from this slide is that improving mechanical efficiency is not only about selecting a good PTO mechanism, it also requires proper lubrication, accurate alignment, high quality bearings, efficient gears and regular maintenance. Even small reductions in mechanical losses can significantly improve the overall power output of a wave energy converter. Now that we have discussed the design and efficiency of a mechanical PTO system, let us examine one of the most important aspects of wave energy engineering operating in harsh offshore environment. Unlike conventional power plants, wave energy converters are continuously exposed to seawater. Such as extreme waves, storms and marine organisms. As a result, the PTO system must not be efficient, may not be efficient, highly reliable and durable. This figure here on this slide summarizes the major offshore engineering challenges faced by PTO systems. Let us discuss each challenge briefly. The first challenge is extreme waves. Ocean conditions are highly unpredictable. During storms and extreme sea states, wave loads can become several times larger than normal operating loads. These large forces can damage gears, shafts, bearings, hydraulic cylinders and generator components. Therefore, PTO designs must be designed with adequate safety margins and survivability mechanisms. The second challenge is the fatigue loading. Wave energy devices experiences continuous cyclic loading every few seconds over months and years, and millions of loading cycles occur. Even when individual loads are small, repeated loading can initiate cracks and eventually cause structural failure. Fatigue is one of the primary design considerations for offshore mechanical systems. The third challenge is lubrication issues. Mechanical PTO systems depend heavily on proper lubrication. However, offshore environments can degrade lubricants due to moisture contamination, temperature variations and prolonged operation. Poor lubrication increases friction, wear and energy losses. Therefore, lubrication management becomes an important maintenance activity. Another challenge is maintenance and accessibility. Unlike land-based equipment, offshore devices are difficult to access. Maintenance operations often require specialized vessels, favorable weather conditions and trained personnel. Consequently, maintenance costs can become a significant portion of the overall project cost. The next issue is reliability and survivability. A PTO system must operate efficiently during normal conditions while also surviving severe environmental events. High reliability reduces downtime whereas good survivability prevents catastrophic failure during storms. These two requirements are critical for commercial development or deployment. We also face the problem of saltwater ingress. Seawater can penetrate seals, bearings, and gearboxes and mechanical housings. Once water enters the system, corrosion accelerates and lubrication quality deteriorates. Therefore, sealing systems and protective enclosures are extremely important. Another major challenge is biofouling. Marine organisms such as algae, barnacles, and shellfish tend to attach themselves to submerged structures. This additional growth increases weight and hydrodynamic drag and maintenance requirements. Over time, biofouling can significantly affect system performance. Finally, we have corrosion. Seawater is highly corrosive to metallic components. Without proper corrosion protection measures such as coatings, sacrificial anodes, or corrosion resistant materials, the service life of mechanical components can be drastically reduced. When we look at all these challenges together, we realize that designing an efficient PTO is only part of the problem. The real engineering challenge is developing a PTO system that can remain efficient, reliable, and maintainable for many years in harsh offshore environment. This is one of the main reason why PTO designs remains one of the most active research areas in wave energy engineering. Let us now look at a practical example of a mechanical power takeoff system through a published case study by Chandrasekaran and Harinder. This study demonstrates how a mechanical wave energy converter can transform the oscillatory motion of ocean waves into useful electrical using purely mechanical transmission elements. As shown in the figure, the system consists of a floating buoy connected to a rack and pinion arrangement. When wave passes through the device, the buoy moves up and down. In response to the wave action, the vertical motion drives rack, which in turn rotates the pinion gear. The rotational motion is then transmitted through chains, then sprockets, gear trains, and speed multiplication mechanisms before finally driving an electrical generator. In other words, the system follows the energy conversion path: wave motion, buoy motion, rack and pinion mechanism, gear transmission, generator, and electrical power. This is an excellent example of a purely mechanical PTO architecture. Now, let us examine the performance data presented in this study. The device was evaluated under a sea state characterized by a wave height of approximately 2.5 meter and a wave period of 7.41 seconds. Under these conditions, the buoy absorbed about 42 kilowatts of wave power. However, not all of this absorbed energy matches the generator because losses occur at various stages of the transmission systems. The buoy efficiency was reported as approximately 21%. This means that only a fraction of the total available wave energy was successfully captured by the buoy. Once energy entered the mechanical transmission system, the performance was much better. The gear train achieved an efficiency of approximately 99% of 99%, then indicating very small loss in gear meshing. Similarly, the chain drive system achieved an efficiency of about 97.3%, which is also quite high. These results highlight an important engineering observation. Mechanical transmission systems can extremely efficient which when properly designed, aligned and lubricated. After passing through the mechanical transmission stages, the generator produced approximately 37.39 kilowatts of electrical power. When all losses are considered together, the overall efficiency of the complete mechanical wave energy converter was reported as approximately 18.7%. At first glance, this value may seem modest. However, it is important to understand that the major challenge is not the mechanical transmission itself. The greatest losses usually occur during the wave energy capture, where only a portion of the available wave energy can be absorbed by the floating body. This case study clearly demonstrates two important lessons. First, mechanical PTO systems are technically feasible and can achieve very high transmission efficiencies. Second, improving the hydrodynamic energy capture process is often just as important as improving the PTO itself. Therefore, successful wave energy converter design requires optimization of both the hydrodynamic subsystem and the power takeoff subsystem. This study remains a valuable reference because it provides one of the earliest detailed demonstrations of a complete mechanical PTO architecture for wave energy conversion. Before concluding this lecture, let us briefly look at some of the emerging improvements being explored in mechanical PTO systems. Although mechanical PTO technologies have been studied for many years, research continues to improve their efficiency, reliability and long-term survivability. One important research direction is the development of low friction mechanisms. By reducing friction losses in gears, bearings and moving joints, more of the captured wave energy can be delivered to the generator. Another area is the use of smart gear systems. These systems can adopt transmission ratios according to changing wave conditions, helping maintain efficient operation over a wide range of sea states. Researchers are also investing advanced composite materials compared with traditional steel components. Composites can reduce weight while maintaining adequate strength and corrosion resistance. Similarly, corrosion resistant materials and coatings are becoming increasingly important for extending the service life of offshore mechanical components and reducing maintenance costs. Finally, considerable attention is being given to hybrid PTO integration, where mechanical systems are combined with hydraulic, electrical or energy storage technologies to improve overall performance and power quality. These developments demonstrate that mechanical PTO systems continue to evolve and remain relevant for future wave energy applications. Let us briefly summarize the key concepts discussed in this lecture. We learned that mechanical PTO systems directly convert wave induced motion into rotational energy. Using transmission elements such as gears, rack and pinion mechanisms, crank slider systems and flywheels. We saw that amplification is often necessary because ocean waves typically produce low speed oscillatory motion. Whereas generators require high rotational speeds for efficient operation. We also discussed the transmission efficiency is affected by friction, bearing losses, gear meshing losses, misalignment and wear. In addition, offshore deployment introduces several engineering challenges including corrosion, fatigue, loading, biofouling, lubrication issues and maintenance accessibility. Finally, we reviewed a real-world mechanical wave energy converter case study and examined emerging research directions aimed at improving performance and reliability. With this understanding of mechanical PTO systems, we are now prepared to explore the next category of wave energy conversion technologies in subsequent lectures. These are few selected references cited in this lecture. Thank you for your attention. Thank you.